Hey, welcome. We're going to talk about the conservation of mechanical energy today. Now, what we mean by mechanical energy is all the potential and kinetic energy in a system. And by system, what we mean is a group of objects that are affecting one another. Okay, and so just in a minute we're going to go over to the barn over there and throw a ball in the air. Simple thing. So the system that we'll be working with is me and a ball. For the sake of simplicity, this yellow line is going to be our reference point. Notice how that's where the ball takes off and where I catch the ball again. So when the ball takes off here at our reference point, since the height is 0, the gravitational potential energy is 0. Then the ball reaches its apex, and when it reaches its apex it stops. So that means the kinetic energy is 0. At that point we've reached a height of 2.5 meters above our reference point. We'll use that later. Then we reach the bottom again, at which point the gravitational potential energy is 0 joules again. So here's what's happening to our energy. We start at a height of 0, and so we have no gravitational potential energy, only kinetic energy. But then as the ball goes upward toward the apex, that kinetic energy that the ball started with transforms into gravitational potential energy. Then the ball falls, and that gravitational potential energy gets transformed into kinetic energy again, until it reaches the bottom, at which point it has all kinetic energy and no gravitational potential energy anymore. So when we do the calculations for energy using mgh for gravitational potential energy and half mv squared for kinetic energy, what we get is about 5 joules. The ball is about 200 grams, something like that. And so we get 5 joules of energy at the very bottom before it has any gravitational potential energy, and 5 joules at the very top when it has no kinetic energy. Right in the middle, that means here where it stops, it's split half and half. We're halfway to the top, and so now we have 2.5 joules of gravitational potential energy that has been gained since the bottom, and 2.5 joules of kinetic energy is left. So the law of conservation of energy says that no matter where you look in the path of the ball, it will always have 5 joules of mechanical energy. What changes is how much of it is kinetic and how much of it is potential. That brings us to the calculations portion. Now to recap, the law of conservation of energy says that energy is not created or destroyed in a system, it just transforms from one type to another. So when I threw the ball in the air, kinetic energy transformed into gravitational potential energy, which then transformed back into kinetic energy. Now you might ask, where did the kinetic energy come from in the first place? Well, that kinetic energy depended on a muscle contraction, and that muscle contraction depended on chemical energy found in ATP. Now, if you're not familiar with ATP, you can look that up online and you'll get a whole bunch of resource stuff about muscle contraction and biology that way. Now, the energy that's stored in ATP comes from food breakdown during digestion, and that chemical energy stored in food, eventually, if you look back far enough, came from the sun. That's where we're going to find the origin of all of the energy that we work with on the Earth. But we're going to look a little bit simpler than all the way back there. Let's think about just somebody snowboarding down a hill. So the example that you have on your page is exactly that. But I want to talk about my friend Ian instead of that particular example. So you know that if you're familiar with hill sports at least, that as you go down a hill, you usually do this thing called carving. It's quick turns that makes sure you're not gaining too much speed and getting out of control. And so that quick turns that you're doing, those quick turns that you're doing, use friction to transform your kinetic energy into heat, thereby making you lose some kinetic energy and keeping you at a safe speed. But my friend Ian doesn't really like the whole carving thing. He just starts at the top, points his short skate skis down the hill, and just bombs down the hill. And then when he gets to the bottom, you can imagine what happens. I mean, he usually can control himself, but he's also a big guy, and so it's a little bit scary watching him do it. So his potential energy at the top is almost perfectly transforming into kinetic energy at the bottom. But for the rest of us who like to carve down the hill, it's not a perfect transfer from potential at the top to kinetic at the bottom. There's this loss in between because we're taking our kinetic energy and transforming it into heat via friction. So mathematically, the conservation of energy can be written like this. We can say that the energy at the beginning, E1, is equal to the energy at the end, E2. And to make that a little bit more specific, the energy at the beginning, since we're talking about mechanical energy, is the kinetic energy and the potential energy at the beginning. So we're going to say that's equal to EK1, the kinetic energy at the beginning, plus EP1, potential energy at the beginning, is equal to the kinetic energy at the end plus the potential energy at the end. Okay, now this potential energy piece over here, we've been talking about gravitational potential energy. So I didn't write EG1 there because that potential energy could be more than just gravitational potential energy. We could be talking about spring potential energy as well. Okay, so we may need to split that EP into more pieces than just the gravitational part. Now, for the purpose of this particular lesson, we're going to leave out spring potential. We haven't talked about that yet, and so we're just going to be putting gravitational potential energy in that spot. Okay, so this says that the kinetic energy and the potential energy at the beginning is equal to the total at the end as well. It's just where that energy is, kinetic or gravitational potential, will have changed. We are assuming in that formula that no work was done, no external energy loss happened. Okay, so the example I gave you about my friend bombing down the hill, some energy was lost due to friction. Okay, friction transformed that energy into heat. We would say that the friction did work on the person because it caused a change in energy. Okay, so the conservation of energy formula there assumes that there is no loss of energy or no gain of energy due to an external force. We can make it a little bit more general by writing the work energy theorem like this. Work equals the change in kinetic energy plus the change in potential energy. Okay, so however much kinetic energy has changed, plus however much potential energy has changed, that total change adds up to the work that was done. Okay, now it could be, in a perfect system, that there was no loss, and so then whatever change there was in kinetic energy would be picked up by the potential energy. So maybe there was a loss of 5 joules of kinetic energy, and then it was gained by the potential energy. So in that case, the work done would still be 0, in which case the conservation of energy formula still works. Okay, and so you can expand this. Work equals EK2 minus EK1, that's the change in kinetic energy, plus EP2 minus EP1, that would be the change in potential energy. Now, if there is no energy lost or gained, then there is no work done, and so we get 0 is the work, and that's equal to the change in kinetic energy plus the change in potential energy. And we can use that to show where the conservation of energy formula comes from, or to show that it's consistent with the work energy theorem. Okay, so if this is the case, we can go 0 equals EK2 minus EK1 plus EP2 minus EP1. Now, if we take this EK1 here and this EP1 here and add both of those things to both sides, just rearrange this a little bit using algebra, what you end up with is EK1 on the left plus EP1 on the left hand side, and then all we're left with on the right is EK2 plus EP2, which is exactly what our conservation of energy formula said, that all of the energy at the beginning kinetic and potential together, is equal to all the energy at the end, kinetic and potential together, assuming there is no work done, and that was the assumption that we started with. Now we'll finish off with a couple examples. A ball with a mass of 0.25 kilograms is thrown downward, not just dropped, from a roof that is 18 meters high. Initially, the velocity is 16 meters per second, so with what velocity does it hit the ground? So here's our situation. Here's a ball. It is being thrown downward toward the ground, so that means at the beginning it's got kinetic energy because it's being thrown, and it also has gravitational potential energy, e.g. Okay, at the bottom, once it has hit the ground, now it no longer has any gravitational potential energy. Now it just has kinetic energy because its height is 0 at the bottom. So when we're going to use the law of conservation of energy, we're going to start off with E1 equals E2. We know that no energy is lost. It doesn't say that there's a loss of energy in the question for some reason. And so we're going to say that the energy at the beginning is equal to the energy at the end. The distribution has just changed. And so we have kinetic energy at the beginning, EK1, and potential energy at the beginning, EG1, and that's equal to the kinetic energy at the end, EK2, plus the potential energy at the end, EG2. Now, we just said that there is no gravitational potential energy at the end, and so this EG2 part over here, this is unnecessary. This is just 0 joules anyway. Okay, so you are allowed to, when you're setting up this equation, account for where is there energy. Is there energy at the beginning? Is there energy at the end? Where is it? You can just decide not to include this EG2 at the end because you know that you just know it's 0 already. Okay, and so now we're going to expand each of these pieces into their formulas. So EK1 is half mv squared, and EG1 is mgh, and that equals half mv squared. Okay, now what we're trying to solve for is the velocity with which it hits the ground. That's this piece right over here, the second v, okay, or the v on the right side of the equation. So this is hopefully going to be straightforward. We're going to plug in some numbers and rearrange. I like to rearrange first and then plug in numbers. I find it a little bit more straightforward, but you can do whatever you'd like. So when we get this v squared by itself, we're going to need to divide by a half, we're going to need to divide by a half, and we're going to need to divide by mass. Okay? So when we divide by a half, that's the same thing as multiplying by 2. So now we end up with 2 times half mv squared plus mgh. I really should say this is mv1 squared and this is mv2 squared. If we get confused that they're not the same thing, we could just end up canceling them out in the end. So we need to be careful about that. Okay, mgh, and this is divided by mass. Now you'll notice that there's mass in every term here, and dividing by mass just ends up canceling these things out. The question did tell us what the mass of the ball was, so you could put it in if you wanted to, but in this case, it's not necessary. Okay, and so our mass gets canceled out. Okay, so now what we end up with is 2 times a half times v squared. I'm going to put the numbers in at this point. So this v is 16 meters per second squared, plus g is 9.8 meters per second squared, and the h is 18 meters. Okay, and all of that together equals v2 squared. Okay, but I'm just going to right away square root this whole thing. See if I can do this cleanly. There you go. I'm going to square root that whole thing to get v2 by itself. And when you do that, you get v2 is equal to 25 meters per second. That's how fast it's going when it hits the ground. And now our final example. What upward velocity must an Olympic high jumper have in order to clear a bar set at 2 meters? Assume an upward displacement of 1.15 meters from center of mass. Okay, now this second part here is important. Assume an upward displacement of 1.15 meters from center of mass. So if you know anything about high jump, or if you've had experience in high jump before, you'll know that when you're running at the bar, I'm going to use red for the person so you can actually see them. When you're running at the bar, like this, there you go. The person's running at the bar. They don't have to like jump their feet over the bar, right? What they do is they jump backwards, and so their head clears the bar, and then they curve their body so that they don't have to jump as high as they would if they were trying to get their feet straight over while staying upright. So then their body position looks something like this. They have their head here, the rest of their body like this, and then their feet something like that. Okay? And what this does is change where their center of mass is. So normally, this person's center of mass is somewhere around here. But when you bend your body like this, now the center of mass isn't even on the person anymore. The center of mass is somewhere over here. Okay? So they have to raise their center of mass just high enough to get them over the bar, but that doesn't mean that they have to raise their entire body that high, because by bending the body, you can change where your center of mass is, so it's actually located outside your body. Okay, and so what this question is saying is that the distance from the original height of the center of mass to the new height of the center of mass is 1.15 meters. Okay, so that's this part over here, 1.15 meters. So the fact that the bar is set at 2 meters, that's immaterial to the question. You really only need the fact that there's a change in height of 1.15 meters. Okay, so we're looking at from the point where this person takes off from the ground, they're going to have no potential energy. Okay, just like when I threw that ball up in the air, the ball wasn't on the ground, but we considered it to have zero potential energy when it was in my hand still. Okay, same thing with this person. Yes, their center of mass is not on the ground. It has a height. We're going to consider it having a potential energy of 0 at that point. Okay, but they do have kinetic energy when they're leaving the ground. So we're at the point where this person has bent their leg and they're about to take off, and so the center of mass now is going to have upward velocity. Okay, so it's going to have kinetic energy. So now we're looking at the law of conservation of energy again. At the beginning, we had kinetic energy, EK1, but we didn't have any potential energy. So I'm not actually even going to write it down on this side. So EK1 is equal to, at the very top, we now no longer have kinetic energy. Now there's just gravitational potential energy, because we're at the apex of the jump. And so this is EG2, gravitational potential energy at the end. Okay, now this is half mv squared, half mv1 squared, and this side is mgh. Okay, notice that in the question it does not tell us the mass of the high jumper. Okay, but it doesn't actually matter because there's mass in each term. Right there and right there. You're going to find that pretty consistently with law of conservation of energy questions, because both of our formulas, the kinetic energy and the gravitational potential energy formula, because both formulas have mass in them, you can just always cancel mass out, no matter what you're trying to solve for, unless you're trying to solve for mass. In that case, that would kind of be against the point. So now we have V1 squared times a half is equal to GH. And what we're trying to figure out is what's the upward velocity got to be at the beginning. So we're going to divide by a half, or multiply by 2, and square root the other side as well. So V1 is equal to the square root of 2GH. Okay, check my algebra if you're not sure. We had to divide by a half, which is the same thing as multiplying by 2, and square root. So this is where we end up. Now G is 9.8. H in this case is 1.15 meters. So now we have V1 is equal to the square root of 2 times 9.8 meters per second squared times a height of 1.15 meters and square rooted. And when you do that, you get V1 must have been 4.7 meters per second. So they had to have an upward velocity of 4.7 meters per second in order to clear the bar.